Now that you've had the opportunity to try a limiting reactant BCA table on your own, we'll go through the answer to this question together. To start off with, I want to let you know that on your test, you can expect two limiting reactant BCA table problems. One where I provide you a starting number of both reactants in moles, and that I ask for your answers to be in moles, and then a second question that is in the same format as the one you see before you, where I give you your starting numbers in grams, and then I ask for your final answers to be in grams as well. We are only going to demonstrate today a BCA table for limiting reactants where I give you grams and then ask for your answers in grams, because if you can do a table this way, you can do the simpler version when I give you moles. To start off with, we always write a balanced chemical equation, so we will have CaCl2 plus MgNO3 yielding CaNO3 plus MgCl2. Our next step would be to balance this equation, but if you count up the number of each type of atom on both sides of the arrows, you'll see that it is already balanced, so all of our coefficients are just 1. Next, we can set up the BCA table itself, but because our numbers are not given to us in moles, we will have to convert the grams of calcium chloride and the grams of magnesium nitrate into moles before we can put them into the BCA table. So we'll start off with the calcium chloride, 18.6 grams. Using your mole roadmap, you'll put 1 mole on top and the molar mass of CaCl2 on the bottom. It's 111.1 grams when you add it up off the periodic table. When you do that math, it gives you 0.167 moles. Then you will do the same thing, but for the 54.2 grams of magnesium nitrate. So 54.2 grams times 1 mole over the molar mass of MgNO3, which when added up off the periodic table is 148.3 grams. That gives you 0.365 moles. Now we are ready to put those numbers into our BCA table. So 0.167 under the CaCl2, 0.365 under the MgNO3, and as always, our products start with 0 moles. The new step for limiting reactant BCA tables is to figure out which reactant is the excess and which is the limiting reactant. So because they all have coefficients of 1, it doesn't matter which reactant we pick, and so I'm going to choose CaCl2 and put the coefficient of 1 over 0.167 and set that equal to 1 over x for the MgNO3. That tells me that x is equal to 0.167, which means if I use up all 0.167 moles of CaCl2, I would need 0.167 moles of MgNO3 to make that happen. Because I have more than what I would need, I have more than 0.167, the MgNO3 is my excess and the CaCl2 is my limiting reactant. I like to write those little notes up above the equation just to remind myself. As always, we are going to subtract our reactants and add our products. And at this point, since we know that CaCl2 is our limiting reactant, that is the amount that we are going to subtract in full. So in our change row, we are going to minus 0.167. We would then need to figure out the change row numbers for all of the other substances based on the limiting reactant. If they all have the same coefficient of 1, we can plug in the same change row number for all of them. So 0.167, 0.167, 0.167 moles. Then to finish our BCA table, all we need to do is complete the math. So 0.167 minus 0.167 is 0. 0.365 minus 0.167 is 0.198. 0 plus 0.167 is 0.167. 0 plus 0.167 is 0.167. Now that our BCA table is complete, we can answer the following questions. What thing is the limiting reactant? Again, that's the one that we use up all of it, and so we have 0 in the after row. So CaCl2 would be our limiting reactant. It then asks for how many grams of magnesium chloride would be produced. So that's our 0.167 number changed from moles into grams. So 0.167 moles. Using our mole roadmap, we would put 1 mole on the bottom, and we would add up the molar mass of MgCl2, which is 95.3 grams. And when we calculate that out, we would get 15.9 grams as our final answer. And then the last question asks how many grams of excess are left over. So when we look at our reactant that is the excess, that's our MgNO32, the table tells us that we have 0.198 moles of it left over, but the answer was asked for in grams, so we take 0.198 moles, and using our mole roadmap, we're going to convert that into grams by multiplying it by the molar mass of MgNO32, which when added up off the periodic table is 148.3 grams. And when we do that math, 0.198 times 148.3 divided by 1, we get 29.4 grams of leftover.